I think we'll start. So, good evening, everyone. Welcome to the fourth episode of the Industry Connect series from SkillX. Through this series of talks and webinars and interactions, we want to bring people from the industry to interact with our fresh talent and thus help further the aim of SkillX to help our youngsters to upskill themselves and eventually get their first jobs. So that is what we aim through this series. I hope you will find this useful and interesting. So today our topic is opportunities in supercomputing and high performance computing, and we have with us representatives from a very interesting company, Smart IOPS, which is based in California, in the Silicon Valley, and also has its engineering team sitting both in Trivandrum and Bangalore. So it's a very promising startup doing really cutting edge work. In fact, the SSDs, the solid state storage devices which they have developed have been benchmarked as the world's fastest SSD drives, which is used in high performance computing applications. And they have some very prestigious clients, including NASA. They're doing work for them in collaborating with these clients. So that is the company that is making the presentations today. And the speakers we have today are Mr. Vishnu AS, who is the technical lead high performance computing and cloud applications at Smart IOPS. He has been with Smart IOPS since 2019. After completing his BTech in computer science from the University of Kerala, he pursued his master's in parallel programming and supercomputing architectures from the Technical University of Munich in Germany. He is an active member of MPI Forum and has work experience in various software companies, including Infosys and Alliance Technology. A very warm welcome to you, Mr. Vishnu. We also have with us today Dr. Shyam Shankar, who is the head of applications and performance at Smart IOPS. He has been with Smart IOPS since 2017. He is an alumnus of the College of Engineering, Trivandrum. He completed his MTech and PhD from the University of Kerala. He has 24 plus years of experience in the IT industry and has worked with various organizations like IBS, Infosys, Verizon, EY, and Alliance, and most of them as an enterprise architect. So very warm welcome to you too, Dr. Shyam Shankar. So I would now hand over to you for doing the presentation. Thank you.
Thanks a lot, Anand. And good evening and a very warm welcome to everyone who has joined. This is a very great opportunity and platform for us to connect with all the bright young minds who have joined, who have registered for this event and who have joined. A very warm welcome and also thank you for joining. So by the way, I am Shyam and I head the applications and performance at Smart IOPS. So the plan for today is that I'll first give you an introduction to the company and our products, and then I'll hand over to Vishnu, our technical lead, to give an introduction to supercomputing and high performance computing. So let me start with an introduction to our company and products. Let me share the screen first. Is my screen visible?
Yes.
Yes, right.
Yeah, so let me start with an introduction to Smart IOPS. So Smart IOPS as a company, you can call it an advanced stage startup. It was founded in 2013. It is headquartered in Silicon Valley, as Anand has already mentioned. Uh, and the interesting part is that the entire engineering and development happens in India. We've got two offices in India, one in Bangalore and another in Trivandrum. And around 50 engineers are working in Bangalore and Trivandrum. And what do? We develop high performance storage solutions. And these storage solutions are meant for high performance computing, supercomputers, and for performance critical enterprise applications. Basically for enterprise data centers. So these are solutions which are used in cases where you need a very high rate of data retrieval and data writing, very high IOPS. So our flagship product or our core of our storage solution is our NVMe SSD. And that is the one which drives the entire high performance storage solutions. And our NVMe SSD is the fastest in the world. And this is not a claim that we are just making. As we progress through the presentation, I will also show you the proof of why we call it the fastest SSD in the NVMe SSD in the world. The interesting part is that a major portion of the engineering and development of the fastest NVMe SSD in the world is done right here at Korongonam in Tirunelveli, and which is something that we should be proud of. And it's based on our proprietary true random technology. So it's entirely built from grounds up. The entire engineering and development for the SSD has come from Smart IOPS. And because this that is why Smart IOPS is a very unique company as such, because we are working in a totally different area to most of the companies that you see. And because we are at the cutting edge of the technology and we develop state-of-art storage solutions, we also generate a lot of patents, and we already have 30 plus patents in the different stages of patent granting pipeline. Several have been already been granted by US Patent Office. And in the next 2 or 3 slides, I will show you why we have such a strong base. I mean, those who are cricket fans here might have watched the recent India-West Indies T20s and seen how Surya Kumar Yadav or Roman Powell hit with such, they hit around the ground with such strong power. The reason that they do so is because of the strong base that they have, their stance and the stability of the strong base. So similarly at Smart IOPS, because this is such a unique area, niche area, to develop such high performance and state-of-the-art storage solutions, you need a strong base upon which we can build this. And that comes from the experience of our founding team. So these are our 3 founders, and Dr. Manuel, Ashutosh, and Radhakrishnan Nair. And they come with a lot of industry experience, tremendous industry experience. They have headed international teams. Dr. Manuel is an IEEE Life Fellow. Ashutosh and Radhakrishnan Nair have not only led international teams, they have successfully launched products which have brought in billions of revenues for the respective companies in which they work. So, and they come with a lot of knowledge and expertise and skill in the area of storage. So that is the base upon which that we have built our proprietary true random technology, which is the core of our NVMe SSDs, which drives the performance of our storage solutions. And it's not just a founding team. We also have an advisory team consisting of a team of very highly reputed names in the industry, who have been founders of large companies, who have been CEOs of large companies, and whose voice carry a lot of weight in the industry. So these are just a glimpse of why we have been able to, develop such cutting edge storage solutions. And because of this strong founding team and the advisory board that we have been able to build this tremendous IP portfolio also. So these are some of the patents that have been granted to us. There are still more which are pending with USPTO, and there are some patents which are under filing also. So yeah, so if you look at this figure that is shown in this slide, so it shows the various levels at which we work. So the storage module forms the building block, of our entire stack, and that is where the most of our engineering and development happens. And on top of that, we build storage server appliances in partnership with a large ODM, one of the largest ODMs in the world. And above that, we develop and build drivers for the applications. And these are fine-tuned for the end user applications. And on top of that, we also develop some applications which make use of all these high performance storage. So the reason for showing this particular diagram here is to show the various levels at which there are opportunities in our organization. So this is a view of the different products that we have right now. So I'm sure you, being engineering students, you've heard of SSDs. These are solid state devices which are in fact, replacing the ever reliable HDDs, the hard drives. And most of the laptops also these days come with SSDs, but our products are not meant for retail consumers. These are more for enterprise data centers and supercomputing, high performance computing applications. So as I said, the flagship product is the data engine SSD, which comes in the half height, half length, or add-in card format, and the 2.5-inch U.2 format. We also have the storage server appliance. We have rack solutions. So this is just a view of what kind of products that we have got, what kind of products that we develop. And our storage solution products are used in many domains. For example, when it comes to high performance computing, it's used in domains such as machine learning, AI, the databases, some of the databases where the NoSQL key value databases where you need very high rate of data retrieval and writing, gene sequencing, the bioinformatics applications, oil and gas exploration, data analytics, etc. And on the enterprise storage appliance, it's used in telecom for content delivery. Recently, we won a bid, an international bid, where our storage appliance with our SSDs were selected and are now being used for a trial run for rolling out of the 8K IPTV of a major international telecom player. So these are some of the domains where our high performance storage applications, appliances, and SSDs are used. And these are some of our major customers and engagements. NASA's Ames Research Center in Silicon Valley uses our storage solutions. Oak Ridge National Lab is one of the world's major supercomputing research center. They are trying out our SSDs. In fact, here, India's own national Param supercomputing facility at C-DAC Pune. For the last 2 years, our Smart IOPS storage server appliance, along with our SSD, is being used there. So this just some of the database benchmarks which show that how our SSDs outperform those of the competitors. I will show you one some a few slides earlier, I made a claim that our SSD is the fastest SSD in the world. So this is the proof of that. Aerospike is one of the world's leading key value database, the NoSQL database, and it's mainly used in the financial security, the advertisement technology, ad tech domains, etc. And they have got one of the industry's best benchmarking tools for benchmarking the performance of storage devices. It's called ACT, or Aerospike certification tool. And this, what Aerospike does is that they periodically run these ACT tests on various storage devices and publish the results on their website. So this is a screen grab which has been taken from their website. You can see the URL also here. So you can go to the website and see that. And these are the results that they have published on the website. And if you see, the top 3 spots are occupied by Smart IOPS data engine SSDs. So this is the proof of the claim that I made earlier, saying that ours is the fastest SSD. And an interesting point to note here is that if you look at the speed, TPS, transactions per second, our SSD is the only one which reaches the 1 million TPS mark. And if you look at the next best, if you remove all the Smart IOPS SSDs and look at the next best, it's almost half of what we have achieved, and that also at a very low latency. So yeah, so that is an introduction to Smart IOPS and our products. I hope that from what I have presented, it has made things interesting for you about our organization and the products. Before I hand it over to technical lead Vishnu to talk about high performance computing and supercomputing, I also want to show you one more slide, which again Vishnu will show it in his presentation also, to reiterate the point, to show where all in which all areas we work, and where all we have opportunities. If you are interested in PCB and system related opportunities, we have opportunities for that. If you have an inclination towards mathematical algorithms and implementation, we have opportunities for that. Digital design, computer architecture, FPGA, logic verification, firmware algorithms, embedded firmware implementation. And not just this, we also have opportunities in the software side, that is HPC application development for enterprise critical applications, the performance benchmarking of these devices, etc. So yeah, so with that, I come to the end of my introduction to Smart IOPS and products. So let me stop sharing and hand it over to Vishnu to take over and talk about supercomputing and high performance computing. Vishnu?
Yeah. Thank you, Shyam.
Yeah.
So good evening, everyone. Now we'll basically look into supercomputers and what high performance computing is. And basically, we will look into few of the world's fastest supercomputers. So let me share my screen first. So is it visible?
Yes.
Hello?
Yeah, we are able to see the slide.
Yeah, thank you. So these are few images of supercomputers across the world. And if you actually search for a supercomputer in Google, these are few of the images that pops up. I mean, more than 80% of the search results in Google for a supercomputer will look similar to these, like long rows of basically cupboards, and nothing makes sense. Like back in our days, when I was doing my graduation, I mean, the only place where I actually hear about supercomputer is in actually Hollywood movies. In these movies where the villain breaks into a high security building, hacks into a supercomputer, takes over the nuclear codes, tries to attack a continent, and now there is a hero coming in and saving the world. But other than that, coming into a technical aspect, the information or this domain of supercomputer was very limited. But nowadays things have changed. Like Shyam has said, like the supercomputing opportunities in India, even in developing countries like India, is marginal. So let's look into each of these pictures separately. So the one on the left, first one is a Syra supercomputer. It's hosted at Lawrence Livermore National Laboratory. So that's basically a lab where they actually design nuclear bombs. At least that's what they say. And this is currently world's third fastest supercomputer. As you can see, like I said, like a long row of cabinets or cupboards. And the second one on the right side, what you can see is called Pugapu. This Pugapu supercomputer belongs to Japan, and it is hosted in an institute called Riken. Again, it's a research organization. And this Pugapu supercomputer is basically the fastest supercomputer in the world. So what you're seeing here is the most powerful machine in the world as of today, and it's in Japan. And they have widely used it for this COVID virus spread simulations and finding the antidotes and all that. The third one is a supercomputer called SuperMOOC. It's in Germany, and it's also hosted in a research institute called LRZ. So the reason, and this, I think in 2019, SuperMOOC was ranked in the 9th position, like the 9th fastest supercomputer in the world. But currently it's in the 27th position, I think. So the reason why I want to include this picture is I wanted to show you how big this room can be, because in these it can be small, but in here you can see it extends like a lot till the end. And it's basically hundreds of such cupboards. Now, this is basically the front view. And if you look into the back side of a rack or a cupboard, this is what you see. So what you're seeing here are basically cables, like a lot of cables. And this is one of the neatest alignment of cables I can see, because usually they are totally so messed up. You cannot see where the cables are coming from and to where it is going. Now, so basically the idea is, this is a supercomputer. This is how it looks. If it's in, whether it is in US or let it be in India, it all looks the same. And you have a lot of cables connecting across these cupboards. Now let's take a closer look into what a supercomputer can be from the hardware point of view. We'll start from the left and we'll move to the right. So on the left is what I told as a cupboard. But what you define technically in supercomputing terms is a rack. This is a rack which you can open and close. And this is basically the backside of the rack. So you can see a lot of ports. So these are basically the LAN ports or the high-speed network interconnects, where you connect the cables like you have seen in the previous slide. And once you open the rack door and take out one tray, you will find such a server in the tray. And this server is what you call a rack server. So this rack comprises of maybe around 25 to 40 of such servers. So it can depend on the size. Now, this is what you call a rack server. And the rear view of this rack server is this. Now, usually when you think of a rack in a supercomputer, sometimes this rack can be dedicated for compute power itself, like only CPUs. Certain racks can be dedicated for storage alone. Maybe you will find certain racks which has only GPUs. So that varies depending on the architecture differences in the supercomputer. But in our case, like in this example, let's take that each rack server contributes to both CPU power as well as storage. So in that case, here if you see, On the front side of the rack server, you can see 24 slots here. And you plug one out, this is what you see. And that is basically a SSD or a hard drive, like any storage drive. So you can basically plug in 24 such drives to the front side. And on the rear side, you see two modules which you can take out. So you plug out one, you open it, this is what you see. So here you have the CPU and the RAMs. So on the rear side, you have the computation, and on the front side, you have the storage. So you plug such rack servers onto racks, and you have hundreds of such racks. The compute power and storage of all these units make the supercomputer powerful. So irrespective of which supercomputer you are looking into, this high-level architecture still remains the same. Let's move to the next slide. So how do you define a supercomputer? It's pretty basic, simple definition. It's a very fast supercomputer. It's a very fast computer that can process a significant amount of data very quickly. Now, how do you measure the performance of a supercomputer? Or how do you say how powerful it is? The metric you use for that is flops, floating point operations per second. So the S in flops is not for floating point operations, but instead it's floating point operations per second. So sometimes you also see the metric written as flop -S. Now, so floating point operations is basically, if you think of like you have to multiply two floating point numbers. So that is basically a floating point operation. So how many such floating point operations can a supercomputer do in a second? That is how you define the performance of a supercomputer. So it's as simple. How many floating point operations you can do in a second? Now, what do you use a supercomputer for? So you can simulate nuclear test. So whenever you design a nuclear bomb, you cannot just go around exploding it, right? You cannot just go around blasting it. It has to be a simulation where nobody gets hurt. And that simulation, you cannot do it in a single computer. You can only do it in a supercomputer. And you expect it to be right. Now, another is map the human brain. So human brain has like infinite number of modules. And each of those are like continuously interacting with each other. So till date, we don't have a complete picture of how our brain works. But scientists are now trying to simulate the human brain, like the full view. Build better and safer cars and aircrafts. Generate breathtaking graphics for movies. So maybe that's something that you're all familiar with. And there is a role of supercomputers in all those. Teach self-driving cars the difference between a garbage can and a baby carriage. So we'll come into that later. Now, so currently, let me tell you how fast the current supercomputers are. So current supercomputers that are being built, not the ones right now, the ones that are being built are in the range of exaflops. So exa is 10 power 18. So that is a supercomputer that can do 10 power 18 floating point operations in 1 second. So 10 power 18, yeah, that's a good number. But how big is that? See, the Milky Way galaxy, our galaxy, is 1 quintillion kilometers wide. So 1 quintillion is 10 power 18. So you see, it's that huge, 10 power 18. And on the compute side, every single person on Earth calculating 24 hours a day for more than 4 years is what an exascale supercomputer can do in 1 second. And this is not a bluff. This is true. So this is how powerful a supercomputer is. Maybe you are getting the picture why a supercomputer can contribute a lot into the economic, social development of a country. Now, moving forward. So in the first slide, I told you, we have the world's fastest supercomputer. We have the world's third powerful supercomputer. So who ranks all these? I mean, they're all lying in different continents, doing different kind of stuff, handled by different organizations. How do you rank them? So there is a community called Top 500. So what do they do is, They run few applications or performance tests on these supercomputers, and they come up with a ranking system, like a homogeneous ranking system. And as per the list published in November 2021, this is the top 5 supercomputers in the world. You have Pugapu in Japan, you have seen the picture, and the power of that is 442 petaflops. So peta is 10 power 15, not 10 power 18. 10 power 18 is exa. So it's like similar to half exaflop. So this is where the supercomputing enterprise have reached. They haven't reached exaflop yet, but probably in the next 3 to 4 months, we'll have an exascale supercomputer. And to achieve this 442 petaflops, they need 7 million CPU cores. So can you visualize something like that? 7 million CPU cores in a single room. Can you imagine the sound it makes? Can you imagine the heating it produces, the power it needs? So that's the fascination of a supercomputer. Similarly, rank 2 Summit, 148 petaflops with 2 million cores, and the power consumption. So the first one is consuming 30 million watt. That is huge. Trust me, this is huge. And then you have US also has the 3rd position, and China has the 4th fastest supercomputer. It's called Sunway Taihu Light. And this is the matrix. Moving on. So sometimes you might hear the term HPC. So HPC is high performance computing, and it's not very different from supercomputing. So there used to be a slight difference like years back, but nowadays they have all converged and it's the same. You can use it interchangeably. Supercomputing and high performance computing, they are all the same. So basically, how do you define supercomputing or high performance computing is the use of supercomputers and parallel computing techniques to solve complex problems. And what are these complex problems? We have already identified, like the nuclear bomb simulation, the car and the aircrafts, self-driving cars. Now, in the first line, I use the term parallel computing or parallel programming. You may all be familiar with the term. I'm not sure if you have it in your syllabus or is it on the postgrad level, but it's a simple concept. It's like, so I always use a simple example and I call it the apple problem. So it's like, suppose you have 10 apples with you and I give you a problem, that is to finish all the 10 apples in one go. Suppose you take around 5 minutes, like an average human being takes around 5 minutes to finish one apple, right? So to complete 10 apples, it takes around 50 minutes, right? Now I ask you to speed it up. Come on, how fast can you eat an apple? Maybe the first apple you can, but what about the 9th apple? You'll be struggling. Maybe you will end up at 40 minutes, but not more than that. So what you basically do is you call up 9 of your friends. So there are 10 of you right now. And then you distribute the data, or what is the data here? Apple. You distribute the data across your friends. So everybody has one apple each. And you start eating. The problem is solved in 5 minutes. This is parallel programming. You subdivide the problem into smaller problems and distribute the problem along with the input data across multiple servers, the servers, rack servers that you have seen. And then computation happens in parallel and you get better performance. So this is as simple as it. But trust me, distributing the data and distributing the problem is not as simple as dividing the apple among your friends. So yeah, that is parallel programming. And maybe in your syllabus, you might have done this using threads, multi-threading in Java or Python. So it's similar to it, but in a supercomputer, it's slightly different. You use a couple of different libraries. Now, coming to the HPC applications. So in India, the most famous HPC applications are weather research and forecasting. So in the news, every day, you see weather predictions. Right or wrong, you hear it every day, right? And then you use computational fluid dynamics. You see, so CFD, so it's basically studying the movement of fluids, like the pressure points, intensity, direction, and all that. So we'll come into WRF, like that is weather research and forecasting in the next slide. But CFD, like it's as the picture saying. So in the first one, it's basically designing a F1 car such that, you know, the air friction that the car is facing is minimal. so that if the air friction is minimal, that means it can go faster with the same power. So this lines you see, it's basically the air intensity and the airflow when a car is moving forward. And this is a ship propeller, like how much water it can push if the propeller fan is designed in such a way. So these are the applications. Now let's move into WRF, like weather research and forecasting. So the reason I'm bringing in WRF is I really want you to understand why we need a supercomputer. So in WRF, we will not look into the normal weather predictions. We'll consider hurricanes. Suppose we have a hurricane in the Indian Ocean. What are the things that we would like to know? So it's in the ocean right now. It's safe. We are all safe. But what we would like to know is, when is the landfall going to happen? When is it going to hit the surface, the land? What would be the direction? What would be the trajectory? And then the last, what would be the speed? How fast will it hit the land? So you need to know all these things. These things, you get it through a supercomputer with an application by the name Weather Research and Forecasting. You call it as WRF. So the example that I've used here is Hurricane Isabel. So it hit Northern Carolina in sometime in 2003. It was like very bad. So this is the satellite image that capturing the Hurricane Isabel when it occurred in the ocean. Yeah. And then with this image, along with some sensor data, you feed it to the WRF application. And then WRF's output will be this one, the middle image. So this is basically the hurricane's track and intensity prediction. So this was here when the image, this is at this point. And after running the WRF, you understand that this will be the trajectory of the storm and this will be the intensity. So the colors you see, the color difference is basically the intensity variations. So now you know, and now you can make the evacuation plans. And this is an image when it actually made, when the hurricane made the landfall. So this is again a satellite image. And with this, you can actually verify that, the WRF prediction was right or wrong. So this is basically WRF. And you see, this is important because let's say you have the image, you realize that there is a hurricane. See, you want this prediction to come up in maybe like 5 or 6 hours, right? WRF, this application should not take 2 days to find this prediction, because in 2 days, the hurricane might have disappeared. It's too late. It's not worth it anymore. That's why. And that's why many countries are building faster computers, because what they could have done in 6 hours, they want to do it now in an hour maybe, because it increases the accuracy. You can try it multiple times. You can try out multiple different things. So that's why you need faster supercomputers. This race will never end. It will just get faster and faster and faster. Now, this is one image to show WRF. So this is basically the hurricane. It's forming. The arrows show the air direction and also the intensity with the colors, and it's moving through the land. Yeah. So this is basically an output of the WRF. Now, so I don't have a title here because it's supposed to be a guesswork. I'll show you this video and maybe you can guess what the application might be. I think the video was a bit faster. Sorry, the audio was a bit faster. Sorry that the audio isn't working. No driver in the seat. So the application is self-driving cars or autonomous vehicles. In our previous slide, we saw WRF. So that is not very real time, right? I mean, it's more, I mean, WRF, the government organizations are running the WRF applications. I mean, it's not really the private sector. Yes, there is private companies who are handling these things, but it's mostly with the public institutions. But self-driving cars, you know, it's something that you're going to see in your street maybe in the next 10 years. So even in this kind of application, supercomputers has its relevance. So before I need to explain further, I can just show you what Tesla. So I'm referring to Tesla here. What a Tesla self-driving car is. So each Tesla car is basically equipped with 8 cameras. They have 8 cameras across the car, and also sometimes, you know, if it's raining or snowing, then the images might be a bit blurred out. So to make sure that the predictions are right, they also have sensors there. So images and sensors. And then the computer within the Tesla car, you have a computer running powerful set of vision processing tools for object detection. And the whole thing is based on deep neural network. Maybe I think that's a term that you all might be familiar with, neural networks. So this is basically another video which would actually show the detection that's happening in a Tesla car. This is basically the Tesla car. So let me just pause it for a second. So what you see on the right side are the output of 3 cameras. So it's continuously recording what they're seeing, it's live motion. And at the same time, it is trying to detect the objects, what they're seeing in the frame. So object detection. So if you're familiar with machine learning, you might understand this. Like for others, this rectangle box is basically objects that the system, the tool has identified. Now, this is happening continuously. This is on the left side rear. This is like on the front. So basically it's capturing, and then the prediction is happening and object detection. And then based on the detection, the computer that's running within the Tesla car makes the decision whether to accelerate or to steer or to brake, etc. Now, till this context, Tesla didn't need a supercomputer, right? Everything is basically inside the Tesla car. But let's think of a case where a Tesla car is not able to identify a baby carriage from a garbage can. So if it sees a baby carriage, it is identifying it as a garbage can. So that can be fatal, right? Tesla car. So this scenario is like kind of, you know, it happens every day. So not exactly the garbage can and the baby carriage. That was just an example, because, you know, real world is, you know, very vast. You cannot just train your model 100%. So it has to be, you know, reiteratively training. Yeah. So in the case, assume that, you know, Tesla car is not able to identify the baby carriage. So basically what you do, the Tesla autopilot system, yeah, that is the main thing that identifies everything that is residing inside the Tesla headquarters. That system, you have to retrain that system so that it can now realize or differentiate a garbage can and a baby carriage. So that retraining has to happen very fast. For Tesla, right now, the data set that they're using for training is 1.5 petabytes. So that's around 1,500 terabytes. You know, so just for the system, just to make the system distinguish a baby carriage, it has to actually go through these whole 1.5 petabytes plus the new data again. And that might take 2 days or 3 days, because if you have run machine learning, you might be sitting with maybe 1 terabyte of data, and it'll still take maybe like 5 days in collab to finish the training model. So think of 1,500 terabytes of data. So now what Tesla needs is, so currently this training is happening in a supercomputer that has 5,760 GPUs. But even with this much number of GPUs, Tesla is not happy with the training speed. Tesla needs the training to happen faster, so that in 6 hours, retraining is complete, and then now the Tesla cars can identify the baby carriage. So Tesla claims that training the model should happen faster, and these supercomputers are not enough, and hence they need a specialized supercomputer called Dojo. So they are building it. Tesla is building their own specialized supercomputer. So you see, supercomputers is not just for the high-end applications. It's coming down to your real world day-to-day life. So let's speak about what's happening in India. In India, in 2015, the Ministry of Electronics and Information Technology, they formed a committee called National Supercomputing Mission, NSM, to install 73 supercomputers throughout the country by 2022. So it's still a work in progress. They are actually in the progress of assembling a lot of supercomputers across the country. Additionally, in addition to this, they also revealed that India plans to develop a exascale supercomputer. So no other information is published on that yet, but probably in the next 4 to 5 years, maybe we'll have an exascale supercomputer. And these are the supercomputers that we have right now in India. So the fastest one in India is called Param Siddhi AI, and it's located in C-DAC Pune, and it's offering 4.6 petaflops, and it's ranked at 89. So you see, the fastest one is in India is only 4.5 petaflops. But the fastest one, the world's fastest one in Japan, it's already in 500 petaflops. So we have a long way to go, but we are on the right track. And the second one is called Pratyush. And then you have Meher. And basically the second and the third computer, you can see, they're basically used for weather prediction. Now, what do we do at Smart IOPS? It's basically a summary of what Shyam has said. We manufacture the world's fastest NVMe SSDs. So when we say we build, we just not assemble. We build everything, end to end. Whatever you see on that SSD, we have built it, right from hardware, PCB, firmware, everything. And we also design and build rack servers to host this NVMe SSDs. So that is the reason why I showed you the rack and the servers within the rack. So we also manufacture these servers. Now, we need to sell it to the customer. For that, we architect solutions for customers with HPC and AI requirements. So we get very specific requirements, like we need a supercomputer, specifically maybe for running a CFD for aircrafts. And then we architect a system with all these hardware we have, plus the software for a very specific need. So the architect is also very important. So we work on that as well. And we have experts on all these domains: storage, networking, CPUs, system architecture, PCB, that's for the SSD, system design, microarchitecture, logic design, logic verification, firmware, development, algorithms, again, all for the SSD, flash memory, full product validation, yes, and applications, databases, performance benchmarking, HPC, AI, software development. We also have software development. We have few software products also. So there is a development in progress. So we have a team working for that as well. And the slide which you already saw, these are basically an overview of the teams and the specializations we need. I think, yeah, that's the last slide. Thank you so much. Thank you.
Thank you, Vishnu. So if any of you have questions, you can raise. Either you can unmute yourself or you can ask in the comment box also. And we are going to, there is one question regarding the participation certificate. We will post the link in the comment box. You can then go and register there and get your certificate. Yeah, the Google Forms link has been posted, so you can go there and we will send the certificates to you. Vishnu, one of the questions which a couple of people asked me when we were discussing about this with students was, is it possible for students to explore this subject in any way, while they are still in college? What are the things they could be learning, or for people who have interest in this field or would like to go for higher studies?
Yeah, that's a very good question. And basically the answer to that is read through a couple of articles. So not really technical documents. Look around what is really happening across the continents. So for example, there are a lot of forums or Twitter accounts. Like one of the example would be HPC Guru. So what they do is, as soon as there is something trending happening in the supercomputing community, they publish articles explaining, what is happening there and what is a trending part. So basically, they actually post at least 2 articles every day. So as a beginning step, what I expect a student like pursuing BTech would ask them to do is to read through these articles, because see, they are not highly technical. Okay, at the end of the day, supercomputer is all about CPU, memory, storage, and interconnects. That's it. It's nothing more complex. So they can easily understand these articles. And from these articles, they'll find terms, like certain terms. Like one simple term would be, in one of the articles, they say dual socket server. So that's basically simple. It's a server with 2 CPUs. But you see the term dual socket server, just Google it out. What is a dual socket server? You will understand. And you do this for maybe 6 or 7 months. You basically have the basic skill set to pursue your studies in the HPC domain. And again, coming to the programming side, what you really need is C programming skills, because most of these applications or parallel programming libraries are actually built on top of C. But the basic C knowledge that you cover in your BTech syllabus is more than enough to understand. But it's important that you understand what is being taught in the syllabus. Once that is ready, that's done. So reading these articles, C programming expertise, and then the concepts are very simple, like operating system, network, computer organization. You look into these 3 subjects, you can look into supercomputing. So basically, GATE syllabus is more than enough to go into this domain. It's really not that difficult. You really have a lot to learn, but that will happen slowly. That's not something you can learn in like 6 months. But reading articles is really interesting, and trust me, everybody in our curriculum, like doing BTech in any branch, they can understand this because they all have experience with computers. It's really not tough. Everybody has a computer at home. They should be able to understand these articles. So yeah, that's my answer to your question.
One of the participants have asked, specifically what articles, how can they get? I think if you could elaborate on that a little more.
Yeah, right. So maybe I'll share it here itself on the chat. I can give you a few articles.
I think you can see the links being shared. So you might want to save it right away because you may not be able to get access to it once we close this session.
So this is the most important, the last one. In Twitter, you can follow HPC group. So that's
I think one trick is on Twitter and LinkedIn. Right. If you follow 2 or 3 people, then the algorithm will learn and start bombarding you with related articles.
And all you have to do is open Google and the search will already be there. Every article is already verified. So it's just a matter of maybe 6 months and then you're already there. Initial 6 months might be a little difficult, but you find the terms, look around in Google, try to see what it is. If you don't understand, leave it. It's fine. But whatever you understand, capture it. And slowly you will grow. That's enough. That's all there is.
Then Joel has asked if there is any scope for mechanical engineers in this sector. So I am myself a mechanical engineer. So.
For sure. Why not? Why not? Because that's what I said. Maybe like, maybe 30 years back then, computer wasn't that, it was very specific, right? It was expensive. Everybody couldn't afford it. But now you all have, irrespective of your background, you have the knowledge about computers. And that's all that's needed. Because supercomputer is just a much more powerful computer. Maybe you don't have to go into the application side, but you can go into the hardware side. You can see, maybe you can think of, let's see, I'm going to give you a simple example. Okay, so the supercomputer, they make a lot of heat. Okay, a lot of heat. So basically, these supercomputers are kept in rooms, and they are like air cooled. But air cooling takes a lot of temperature, right? It consumes a lot of power itself, because basically, in addition to running the supercomputer, you also need power to cool down the supercomputer. So maybe why don't mechanical background people run on these kind of architectures? Maybe design the airflow in the room in such a way that it's limited, or maybe build a rack that can support liquid cooling, something like this. So it's not just about programming. This is vast. You need engineers across domains to build a supercomputer, because if you actually look into this supercomputing centers in US, like the Lawrence Livermore or Oak Ridge, you find people from every domain working in this. Because it's not just a domain that is specific to computer science.
Yeah, whoever asked, I'm also a mechanical industrial engineer, basically mechanical. We have scope everywhere, don't worry. Another thing is that CFDs, there's a lot of scope for mechanical engineers in CFD, which is an HPC application. I'm sure you would have heard of CFDs. So while designing fast motorbikes, cars, etc., there's a lot of HPC CFD applications that are simulated, and so that is one thing. And second is that even in at Smart IOPS, as Vishnu said about cooling, so even for our SSDs, it generates a lot of heat. So we have mechanical engineers who design the SSDs, so using CAD and also in such a way that it is cooled properly, because because of its high performance, generates a lot of heat. So mechanical engineers are crucial in every field.
Thank you. Any other questions, friends? So again, Joel has asked, as mechanical engineers, what skills should I learn for entering this sector as a beginner?
Just understand this basic operating system concepts, like operating system and computer organization, but not into the a level a computer science engineer knows, but just the basics, like how an operating system works and all that. Like you have a laptop at your system at your home, just understand how it works. That's enough. and C programming, like I said, because the C programming skills will also help for your CFD if you're working on those domains, AutoCAD, everything. Because you might need to fine tune these simulations, like even the CFD simulations, you might have to. And for that, basic C proficiency will be good.
I don't think we have any more questions. So probably then we can wind up. Just a moment. On YouTube Live, Srinath is asking if there is any scope for BSc Physics graduates.
Physics. Doesn't the CFD all comes in like physics? I mean, you simulate these. I mean, if you design a turbine or a pipe flow thing, I mean, doesn't physics has a role to do in that? I mean, like the air pressure or a fluid pressure at some points. It's all physics, right?
I know at least one person who who's a physics postgraduate and now working with ISRO on weather prediction. So they run some of their models on not really a supercomputer, but some of those high performance computing systems. At least I've heard about that. So that person is a BSc, MSc Physics graduate.
Oh, and another example I can give you is like this. There is one there is a recent thing coming up is like one supercomputer is gonna simulate the entire is going to build a 3D map of the universe. So all these applications, they use physics internally. It's either theoretical physics or astronomical physics. So the applications that you run on a supercomputer comes from different domains, like Shyam said, can come from mechanical or can come from physics or from chemistry. Like if you look into like this protein synthesis, those kind of, you run those kind of applications also in supercomputer, right? So if you want to run protein synthesis in a supercomputer, you need someone who will understand what protein synthesis is, and then another guy who knows how to run this in a supercomputer. So, but you can be a guy who knows both. So there are a wide range of applications that are being run on a supercomputer, and because of that, across domains you have opportunities. Trust me on that.
And another question which has come up is, what are the factors of an operating system which is specific to supercomputers?
That's a very good question actually. So usually on supercomputers, there are certain nodes where you actually run a proper operating system like CentOS, or not usually Ubuntu, but you usually go Fedora or CentOS. But that's only when, so there are few nodes, few servers in a supercomputer where you log into, and then you submit the job, and then the supercomputer takes the job and then runs it. So on the nodes, on the servers where you log into, you might see CentOS or Fedora. But on the other nodes, there is just a minimalistic version of an operating system. It's not the operating systems that you usually deploy in your desktops or PC. That's not the one, because let's assume that in one server, you have 20 CPU cores and you run Ubuntu on that. See, Ubuntu itself will take 2 of those 20 CPU cores for running Ubuntu itself, right? So that's not what you want. So basically, in these servers that are contributing to the supercomputer, you run a very minimalistic version of the operating system. And that's very different from what you're running in your laptop or your PC. Did I answer your question?
I think that should get somebody directed in the right way to start exploring more about different versions of the same operating system and the variants and how it affects. Somebody is asking if only freshers can apply or can. So I think Udni is an MTech graduate in cybersecurity domain, and he passed out in 2017.
Please go ahead. Please apply.
The certificate of attendance will be emailed to you in a couple of days. We will send it. I think that's all the questions we have. So let me once again, thank the Smart IOPS team, both Shyam and Vishnu for this wonderful session. This is a very interesting application, and not something we all get to see on a day-to-day basis usually. So it's been even for me getting to hear about these applications firsthand. It's been very informative and interesting. I'm sure our friends also who have joined would have enjoyed it, and I hope you would all take inspiration from what has been said, and start reading some of those articles, exploring those forums and communities where these topics are discussed. Read more, learn more, and then I think you would be able to get into areas of your passion. Not just this particular subject, but I think it is a little more generally applicable. Keep learning, and we'll be able to follow our dreams. So thanking you all once again, and a big thanks to the various members of faculty, the placement officers who helped us to promote this program, and a big thanks to all the students and other professionals, people who have turned up to listen. So thank you all. Thank you very much.
Thank you very much, Anand. Thank you very much, Trinity, for setting up this wonderful platform and opportunity for us to interact with the bright young minds. And for all the students who joined, if you are interested in any of the areas in which we work, please do get in touch with Anand and Trinity, and please do apply. We've got a lot of opportunities, interesting opportunities, which are very unique in the industry. So, yeah, thanks a lot for joining.
So, thank you, Shyam and Vishnu, and thank you all. So we will have follow-up webinars coming up on various topics. So we will keep you all informed. Thank you.